Oh my God! So, did you see Colin broke the leg off?
Yeah.
Okay. I hate to interrupt, but I'm going to interrupt because today's lesson is a long one. We're gonna try to get through it, and if we don't, whatever, we'll finish it later. But yesterday we talked about equilibrium, and I want you to imagine that we have some reaction here where we have something A reacting to become something B. Actually, I'm sorry, I'm going to change my color code here. No, it doesn't. You're writing an A and a B. You're not using colors. It doesn't affect what you're doing. It only affects what I'm doing because I'm using different colors. Did you use red and green to do that? Good. Now they match.
This like went from like conversation to.
There we go. So there we go. Now, between these two things, I've drawn two arrows. Why have I done that? Yes.
To show that they're going to go back and forth between each other.
Good. And this is a convention you're going to see. I draw two arrows because the reaction can happen forward, as we see with the red arrow. The red arrow tells me that A can react to form B. But the green arrow tells me that the other reaction can happen, and that is B reacting to form A. Does that make sense to you? Glad it makes sense to one of us. Now, if I started just with A, which of those two reactions is the only one that can happen? A to B, right? If all I have is A, it can only go in one direction. As that reaction begins happening, will it get faster or slower? It's going to get slower. It has to get slower because it's decreasing the concentration of A as it goes, right? So reaction A is going to start going as fast as it possibly can, and over time it's going to slow down. And eventually, we said it's going to reach a steady state. Because while that is happening, as soon as A starts making B, what can happen? Yeah, the other reaction can happen. B can start making A. But of course, it's going to start going quite fast. At the beginning? Yeah, it's going to start going quite slowly, actually. Right? But then slowly, it will speed up, speed up, speed up. But eventually, it will stop speeding up, and it too will reach a steady state. And we said, and by the way, I want to be clear, we're not talking about concentrations here. This is the rate of the reaction. That's why I changed the colors, because I didn't want the color of A to be red. I wanted the forward reaction to be red. So this is the forward reaction. And the green line represents the speed of the reverse reaction. The less common spelling of reverse with an F. There we go. When they hit the same speed, what do we call that state? Equilibrium. Now again, I want to stress, this isn't the concentrations. Do we know that the concentrations will necessarily be equal at equilibrium? No, we have no idea. We're going to talk about that today. But we know that at equilibrium, the two reactions will be happening at the same speed. Now, at equilibrium, the concentrations aren't necessarily equal, but at equilibrium, the concentrations will do what? Yeah, they'll remain constant. Once we're at equilibrium, the very definition of equilibrium is the concentrations are going to stop moving. In other words, if I'm on my treadmill, if I go to the airport, I'm on the walking sidewalk. You know the walking sidewalk at the airport? You ever walk the wrong way on the walking sidewalk? Oh, you've got to. There's something fundamentally fun about, people have spent tons of time building this technology to do something, and you're just canceling, thousands of hours of work and thought and engineering just by walking. You're rendering their work useless, which for some reason feels good. But then secondly, the looks you get from people walking the wrong way on the walking sidewalk are pretty priceless. You know, these people running to the plane and you're just casually strolling opposite. But when I reach equilibrium with the walking sidewalk, I am moving, the sidewalk is moving, but somebody from the outside would see my location fixed in place, right? I would appear to be still, flailing, but still to a passerby, right? That's the same thing here. Both reactions are happening, but the concentrations appear constant. Because as quickly as they're being made, they're being used. As quickly as they're being used, they're being made.
So if you were using a reaction like you did a reaction, you wanted to use the products of it, when they're constant and you could separate if you could separate both of them.
We're going to talk about that. I'm going to cut you off only because that question is exactly where this lesson leads, which is a great question. That's precisely the right question. It's like about 12 minutes too early.
Okay.
So there's going to be a moment where I point at you and glare, and that's when you ask that same question. Okay? Beautiful. Now, what I want to say is that at equilibrium, we said the forward rate is equal to the reverse rate. So let's say that at equilibrium, the rate forward is going to be equal to the rate in reverse. Now, I want to imagine this for a nice, simple reaction. We're going to start with something simple and then move to something harder. So I want to imagine some reaction where we have A plus B gives us C plus D, but everything, because we're talking about rates now, right? So I want to imagine for this that all of the rates are just first order. So A is first order, B is first order, C is first order, D is first order. One-step reaction, first order, simple, plain stuff. In that case, looking at this reaction, what would the forward rate be equal to?
K times.
Yeah, I'm going to say some K, and I'm going to call it KF for the forward K. And then times the concentration of? Yeah. Good. And because we're using a nice simple example, everything's first order. Okay. Somebody else, what's the rate of the reverse reaction going to be equal to? Yeah.
KR times concentration of C times concentration of D.
Good. Getting bored. Good. Does that make sense? All we've said is if the forward rate and the reverse rate have to be equal, we can go back to our knowledge of rate laws, and knowing that this is a nice simple reaction, I can write it just like that. Now, if this is true, what if I wanted to put all of the constants on one side and all of the variables, all of our unknown concentrations on the other side? How could I rearrange this? Well, the constants aren't variables. We don't know them. We don't know what they are. But if you think in terms of like y equals mx plus b, y and x are your variables. M and b you may not know yet, but they are a constant value. Once you know them, they don't change. So if I wanted to put all the constants on one side and all of the variables on the other, by convention, what side do you think I'm going to put the constants on? Left, actually, yeah. So let's see if you can do that. Put all of the variables on the right, all the constants on the left. See what you come up with.
Nearly ran over a crossing guard this morning. Nearly ran over a crossing guard this morning. I was angry though because I was waiting for a while. And of course they're like crossing the street. Stupid sign holding up. It's just kind of. I'm in the
If not, I think I have one roll.
I'm just like, no, I'm gonna go. And then she starts to cross back, and as I'm going, she's like, and I'm just like, I'm not saying sorry, so I'm just going around the corner.
Focus, do math. Okay, so I want to put all the variables on the side. So if I want just the variable here, what do I have to move?
Which is the variable?
The k's. Oh, sorry, I'm so sorry. I want the constants on the line. And k's are constant. So over here, what do I have to move?
That over there.
Okay, so this gap is over here. When it goes over here, it will end up on the bottom, right? Because we're going to divide by it. I have to move these over here. They will end up on the. Good, do that.
Okay, well, that's a lot easier than I thought.
McGowan, do math. Okay, be quiet. Still be quiet. Still be quiet. Continue to be quiet. Actually, let's readjust this. Begin being quiet and then continue being quiet. Questions? Good. Oh, that. Thank you. What equation did you get here?
I got Kf over Kr equals concentration of C times the concentration of D over the concentration of A times the concentration of B.
Very good. Thank you. Okay. Now, this, keep in mind, is only true at equilibrium, right? It is only true that the rate of the forward reaction is equal to the rate of the reverse reaction at equilibrium. So this is only true at equilibrium. And so to say that, let me first ask you this. If I divide a constant by a constant, I will get a number that is also a constant. Does that make sense? If Kf is always 6 and Kr is always 2, Kf divided by Kr will always be 3. Because the numbers themselves don't change. Is there any value putting a constant divided by a constant over and over again, writing two numbers when I could just write one? So we're going to rename this. And since we're doing equilibrium, we're going to call it the equilibrium constant. Seems to make sense, right? So we're going to define this as capital K EQ. And we use a capital K just to differentiate it. All right, just to differentiate it from the rate constants where we typically used a lowercase. And then I want to say that the equilibrium constant is equal to the concentration of C at equilibrium. I can't just take any concentration of C. I have to wait until the reaction is at equilibrium and then measure its concentration. Likewise, I have to wait until the reaction is at equilibrium and then measure the equilibrium concentration of D, and for A and for B. Now, this is a nice simple example where everything was first order and we were able to calculate it thusly.
But it gets ugly.
It doesn't get ugly, actually. It gets really easy, but it does require you to accept a black box. And I hate black boxes in science. When I say black box, this is anything in science where we tell you, you take this information and you rearrange it and you write it like this, but we don't tell you why, right? We just tell you, put it through the thing, rearrange it, put this number here, put that number there. Unfortunately, I'm going to have to do that for you, all right? So for a nice, easy example where everything is first order, we can do this math and come up with this equation. Yeah?
Okay, so when I rearranged it, I put KR over KF.
Also true.
So would I just have...
What you would have found is the KEQ of the opposite reaction. So if you went up and instead wrote this as C plus D yields A plus B, that's the KEQ you found. Just as true, just as meaningful, perfectly mathematically valid, but by equilibrium in either way. So by convention, we put the forward reaction on top and the reverse reaction on the bottom, but that's merely a matter of convention. What you did mathematically, 100% correct. So we're going to talk about the law of mass action. And this is, sometimes we do a lesson where the whole first page is about kind of why something works and the concept. But then for those of you who are like, hey, what do I actually have to know to answer the questions you're going to ask? For those of you who are like that, you can essentially only ever look at this note starting on this page, because this is the page where we actually talk about what we're going to use. The first page is kind of the background, the underpinning, explaining why it works. Starting here, we're talking about what we actually use conceptually. All right? The law of mass action says that for any ideal gas or ideal solution, in other words, under ideal conditions, if the system is at equilibrium at a fixed temperature, the product of the equilibrium concentration of the products divided by the product of the does anyone know what that means? I don't. Can I just give you the equation? Great. So we're going to imagine any reaction, and I'm going to say we have a number of moles. This is the coefficient of something A. So the small a would be, if we were talking a balanced chemical equation like 2H2O, the small a would be the 2. And the big A would be the H2O. Can you picture that? Plus B moles of something B, and I'm going to stop at 2, but this would be just as true if there were 7 of them, gives us C moles of some species C and D moles of some species D, and this is in equilibrium. For any reaction that satisfies these conditions, in other words, any reaction, I will kick you, at equilibrium, then we can solve for the equilibrium constant by putting the concentration of each product. In this case, what are the 2 products? C. C and D are the products. And here's where you're going to get mad at me, I hope. Divided by the concentration of the reactants to the exponent of the coefficients. Why are you going to get mad at me? Sorry? That's right. So when we talked about rate laws, I made a point of saying over and over and over again, don't look at the balanced chemical equations, the coefficients don't tell you. And now here I am saying, oh, but when we take the 2 rate laws and set them equal, all of a sudden magically, black box, poof, wow, we get this equation where how do we get the exponents?
Looking at the balanced chemical equation.
Looking at the balanced chemical equation. Here's why. Bear with me. Right? This is before you throw stones at me. In the rate laws, if all things were equal, you actually would look at the coefficient to give you the exponent, even in the rate laws. The reason for the rate laws it doesn't work, and this is kind of weird, and there's a reach ahead lesson that's going to get posted, should have been posted last night, but I didn't. For this, is that when we calculate the rate, most reactions don't actually happen all at once. In other words, for this reaction to happen, first A has to collide with B, and maybe that makes B split into 2 things. And then A has to collide with one of those, and maybe that splits A into 2 things. And then one of the halves from A has to collide with one of the halves from B. And it's these steps that have to happen one after another, after another, after another. Can you picture that? So most reactions, even though we write them as one step, actually have these intermediate steps. We don't write them because they end up canceling themselves out, and it would make it very long and complicated. Yes?
Like cellular respiration, how it's like that's just, in a way.
Yes and no. No, in as much as the difference is those are complete reactions.
Yeah.
It's the same idea, except that these can't stop in the middle.
Okay.
Once the reaction started, it will finish. Whereas cellular respiration, you could stop at any one of those steps. But it's the same principle.
Okay.
That first this happens, then that. But look, just bear with me because it's a little confusing. But each of those steps has its own rate law. Bear with me. This is key. And I know specifically this will bug you too, because there are people who like to understand things as opposed to just write the equation down, right? So here's what I want to say. If you looked at all of those rate laws and added all of those rate laws together, you would end up with the coefficients making the exponents. But what we found out is just like, if you are in a 3-legged race, you ever done these things? Where you tie your leg to somebody else's leg and you have to race? If one of you is really fast and the other one of you is really slow, how fast are you going to go?
Not very far.
You're gonna fall over.
You can only go as fast as the slowest person. Likewise, does that make sense? Right? Like, if we have to lock arms and go on a race, you could be like Usain Bolt. We're not winning. Not gonna happen. I'm gonna pause in the middle and rest. And you're gonna have to pause in the middle and rest with me. So when we did the rate laws, we actually calculate the rate law. Listen again, because this is kind of weird. We actually calculate the rate law for only part of the reaction, the slowest part of the reaction. And that's why we couldn't use the coefficients to predict the order, because we actually don't calculate the rate of the whole reaction. We're calculating the rate of just one little sliver of the reaction. On the other hand, when we get to equilibrium, all steps of the reaction have to be in equilibrium. If it's a 6-step reaction, all 6 steps have to be balanced forwards and backwards. And as a result, unlike when we calculate the rate of an equation, we actually would have to build a rate law for each of those steps. And when you build a rate law for each of the steps and mathematically combine them, it always ends up working out that the coefficients become the exponents. Again, if all of that confused the heck out of you and you weren't bothered in the first place by the fact that I told you to use the exponents, then don't worry about it. Doesn't matter. This is what you do. But if you're someone who likes to understand why, that's the understanding of why. And if you wanted to, I could even sit down and walk, I'm not going to do it here, but I could sit down and walk you through a mathematical example and actually show you why this works. It does work. It's not a paradox. It seems paradoxical because I've only told you half of the story with rate laws. Is that fair? Okay.
So, the fact that both the rate law things are equal, you can use those sort of coefficients, but one is not necessarily equal.
Exactly right. So the rate law, ironically, is only the rate law of part of the reaction, whereas this KEQ deals with the entire reaction, and the coefficients become your exponents. So this is much easier. How did we have to get the exponents for the rate laws? Experimentally, you had to look at the table and say, if I double this, what happens to that, and all that nonsense, right? What do you do here? Look at the equation, stick the number up in the exponent. So this is much easier. With that in mind, we're going to look at a reaction that happens in a gaseous state. Down below, example 1. And I want to just clarify something here. I understand that talking about concentrations of gases is a little bit flimsy, but just do it. Just bear with me. I want you to write the KEQ equation for this reaction, where C2H2 reacts with 5O2 to give us 4 CO2 and 2 water. All right, so go ahead and write the equilibrium equation for that reaction. It's the same principle as above.
But we don't have a value for the concentrations.
I just want the equation.
Oh, okay.
Yeah, that's a great. Yeah, you're not gonna. Are you gonna be able to solve for the number of KEQ here? No. You're just gonna give me the equation, and that's okay. When we actually get going with this in a couple of days, you'll see that you would find KEQ by going and looking at the published values, just like the delta HF values were published, just like the C values were published. They're all things that people have figured out.
Does the water work in here again?
Yes.
Okay, good.
Yeah, you can inside. Whatever you got.
Yeah, I suppose.
Good. Hold on. Hang on, let's see this thing. Good. Very good. Marshall, how do you feel about writing that on here? Cool.
So,
Oh, jeez.
on the,
We're breaking it.
has everybody read the test?
No.
Okay, so I think we
You have to ask. Okay, so look else right here. Hopefully you see that writing an equation in this case, not very challenging. Is it? No. You put the concentrations of the products on the top, the concentrations of the reactants on the bottom, you look at the coefficients and you make those the exponents, and you're done. No, that's the nice thing.
Oh,
You're
no, the way
really
you
done.
said it, it seems really easy, right?
No, it is. It's trivial. It's very simple, very straightforward. Now, are we going to do a little bit more advanced math a little later on? Yeah, but here's the deal. The hardest math you'll do in this course is this unit. And you know what it is? You're going to use the quadratic equation.
Oh, God, I hate that.
Why? It's so easy.
Yeah, but it's,
Negative b
Why
plus
does
minus
it
k,
have
b squared minus 4ac all over 2a.
yeah.
You have two values of x. One will be ridiculous.
Can
One
we
will
just
make
use
sense.
Desmos
One
plot
makes sense,
the
and those are x.
equation and go from there?
Oh, they call that the determinant, I think?
The
Discriminant, that's it, yeah. And you can predict from that how many answers you
roots
have.
you'll have.
Blah, blah, blah. Not a math teacher today. I teach math, I have to worry about that crap. Oh, by the way, just to be clear, like, do you know, because you do actually have to do this stuff in lab. You know what I do in lab? Because I actually do it back there when I prepare solutions sometimes. I go into Desmos and I don't graph it. I I set up a pre-done quadratic equation thing. So all I have to plug in is A, B, and C, and it gives me the X values. Boom, done. So you make a slider for B, a slider for C, a slider for A, plug the numbers in, it spits the answers out at you.
We did that with Wolfram Alpha.
Yeah, same thing. Like, we're science people. The point here isn't to show me your masterful algebra skills. You'll need to use them, sure. But when we can get away with not using them, use technology. We're interested in the application of math here. Now, I want you to do the same thing for the next example, where PCl5 in aqueous solution decomposes to make aqueous PCl3 and aqueous Cl2. We'll get there. So I want you to write the KEQ for this next one as well. But make sure you leave yourself a bit of space because we're going to plug numbers in this time. But first, write the equation for me. Just write it relatively small because you're going to, like, even I would probably, just like here, we'll do another equal sign. We'll actually put the numbers in. So you'll need that much space again.
Oh, okay. I thought we were on this one now.
We are. We're on the next one. But I'm saying just like how the space you left above would be plenty.
Okay. Oh, got it.
So when there's only one, is you only put like.
Yep.
Yeah. Yeah. I mean, if you want to think of it this way, like, I guess the value of little b is 0, right? But just don't worry about it. Like, I used 2 on the left, 2 on the right as the example because that's pretty common. But you can have as many on the left as you want, and you just keep stringing them along. And you can have as many on the right as you want. You just keep stringing them along, or as few.
They don't have to have the same number on one.
Nope, not at all. Great question, by the way. Okay, so the KEQ in this case would be equal to what?
Concentration of PCl3 has a concentration of Cl2 over the concentration of PCl5.
Great, and in this case, what are my exponents? All 1. Okay, does that make sense? Cool, yeah. Now, I want to mention specifically that it mentions the temperature. Is the temperature involved in this calculation?
No.
No. But I mentioned the temperature because the KEQ will change if we change the temperature. So I've mentioned it specifically here to say that all of this happens at 24.2. We can calculate the KEQ of this reaction at 24.2. If I went and did this reaction again but kept it at 18 degrees Celsius, would it obey the same law? Yes and no. It would be the same law, but I would have to solve for a new KEQ because it won't be the same. And we're going to talk specifically about how that changes on the next page. But I just want to make a note of that this all assumes that we're keeping temperature constant. So let's plug numbers. What's the concentration of PCl3 at equilibrium? Yeah, and keep in mind that we have to plug equilibrium values in here, right? In other words, when you do the Reach Ahead Lab for last unit, we're going to use this device here, and it's a colorimeter, and you perform your reaction in a small cuvette, basically a test tube that sits inside here. This shines light through it, and it can tell you the concentration of your reactant based on how much light shines through it. Right? And it makes a graph of it. When you were doing the reaction in here, you wouldn't take your measurement until that graph levels off, right? So when it is steady, then you know you're at equilibrium. As long as it's changing, you have not yet made equilibrium. Does that make sense? So in this case, the equilibrium concentration of PCl3 is what? 0.25 moles per liter. Good, 0.25 molar. And what's the sorry? Molar means moles per liter. That's right. What's the concentration of Cl2 at equilibrium? Also 0.25. Cool. And what's the concentration of PCl5 at equilibrium? There we are. Good. And if we actually do that calculation, what do we get? So and how many sig figs should we have? 2. So 0.42. Good. What will the unit of this be? Yeah, moles per liter or just molar. Right? Because the one of the ones on top will cancel with the one on the bottom. we'll be left with molar on top. Will every KEQ have the same units? No, it totally depends on what the actual equilibrium equation is, right? If one of the ones up top had been squared, then the unit here would be molar squared, right? If there had been more on the bottom, it could actually end up being 1 over molar, or 1 over molar squared. Does that make sense? So the units will change depending on what the actual equation is. Yes? It could not have a unit, yeah. That's exactly right. So KEQ's units are just designed to cancel the other units in the question. They're not really, it's hard to think of them as having a real world meaning. Oh, I got you. Okay. Don't believe me, I know that feeling. Does this make sense? So we can calculate the equilibrium constant if we know the concentrations at equilibrium, which in the lab we would do with a device like that, by measuring them. Now this brings us to our third page, the last concept, and it brings us to Lucia-Talia's principle. But listen, I like to think of Lucia-Talia's principle as the young children principle. That's it. So no. Shall we do lesson in French?
No.
I had to teach science in French for a week once, and it was hell. I didn't do it in French because I only speak very, very, very weak restaurant French, as in like, that's about what I know. Yeah, je n'aime pas le poisson. Pas bien. And that's about it. But anyway, Lucia-Talia's principle has to do with what happens if we take a reaction that is at equilibrium and we change something. Obviously, if I change something, the reaction is also going to change. So first I want to imagine my moving sidewalk. Imagine I'm at the airport, got my elbows up and I'm walking the wrong way on the moving sidewalk. Because I can. Until security asks me to stop. But let's say security, instead of asking me to stop, which is very boring, no, let's say I have a bit of a sense of humor. Because if I were in security, I feel like I would have a sense of humor. I could go up and say, hey, you've got to walk the right way on the moving sidewalk. Or I could crank the speed up. Isn't that way better? I think that's way better. You got some idiot walking the wrong way on the moving sidewalk. So I'm walking the wrong way, and so someone over there just still, right? And then Jimmy, the security guard, cranks the speed up on me. What's going to happen? But before I move faster, I'm going to start moving backwards. And then, yeah, I'm going to catch up. And eventually I'll be going the same speed as it again, right? Or I'll fall. Let's assume I don't. I'm pretty fit. So, I mean, assuming I didn't just decide to do a cartwheel and get out of there, which, I might. But some result, I don't know. But yeah, it's going to speed up and it's going to move me back. And then I will re-establish equilibrium. Can you picture that? Eventually, I will end up moving the same speed as it again. But in the meantime, my physical location has actually changed. I've moved back. Can you picture that? So I've moved back, but then I'll speed up to catch up. But I'm not going to go back to where I was. I'm just going to catch up and go. And so even though eventually I reestablish equilibrium, I will have moved back. If, on the other hand, he had slowed it down, I would have moved forward, and then I would have slowed down as well. So eventually I will again match equilibrium. But before I meet equilibrium, my physical position will have moved. Equilibrium in chemical reactions works the same way. Eventually, equilibrium will be reestablished, but before it is, the concentrations will have to change. The reaction will shift left or shift right. In other words, we'll end up with more products or more reactants, depending on what it has to do to counteract. Now, I said I like to think of it as little children. When my kids were little, they had this amazing ability to always want to do exactly what you don't want them to do. Guys, we're at a funeral, be quiet, chatter. Guys, we're at the border, and the guy's going to ask if I'm your dad. Speak. Do you know this man? All right. We need to put your snowsuit on to go outside to walk you to school. I have to go to the bathroom. I want you to go to the bathroom. And you're putting your snowsuit on. We're going for groceries. I want you to get in the cart. You finally get them in the cart. You go around and get groceries. Now you say, I want you to get out of the cart because we're going to go home. And they're gripping onto the cart like it is the most precious thing in the universe. They're essentially horizontal and you're pulling and it's awkward. The only thing holding on is we've talked about the chain on the corridor, which is its own issue. And it's this big thing. And you just think, I should just let go, but you can't. And you know you can't. And so you talk them down. And kids will always work to exactly counteract what you're trying to do. Reactions are the same way. They always work to counteract what we're trying to do. So I want you to imagine that we have some, there it is, that we have, thank you, that we have some chemical reaction, A plus B, oh sorry, let's make it even easier. Let's just say A forms B, and of course it's at equilibrium, so B can go backwards and form A. You picture that? All right, now, it's at equilibrium, which means that A is being used up at the same rate it's being made, B is being used up at the same rate it's being made, all the concentrations are constant. So if I put it in my little colorimeter over there, the graph would be a straight line. You picture that? You can picture the graph on the computer. You know, at first it went up, and then boom, now it's straight, it's just steady, it's not changing. What would happen if I took a little eyedropper and I put a little bit more A in? Obviously, A is going to go up. Which way is the reaction going to shift? The reaction is going to work to undo what I've done. So I've added A, so the reaction is going to shift to try to make more B. And the whole reaction will shift to the right. The reaction always works to undo what you've done. Does that make sense? So if I increase the concentration of A, it drives the reaction forward. What if I increase the concentration of B? It'll drive the reaction to the left. It'll drive the reaction backwards to try to make more A. Now, you may be wondering, because I wondered this when I first learned this, if all reactions are equilibria like this, how do we get a reaction to go the whole way? Because if I'm in the pharmaceutical industry and I'm using two things that are poisonous to make one thing that is a medicine, it's going to be pretty inconvenient if when I go to give medicine, it's half poison, half medicine. It's a problem. Right? How do we get a reaction to go the whole way? What if, as the reaction's happening, I'm removing B? What if, as we go, I keep taking B away? It's going to drive the reaction to the all the way to the right. This, for example, is why a precipitation reaction keeps going. Remember when we mix things and we got a precipitate to form? That reaction goes all the way, because as the precipitate forms, it's no longer aqueous. If it's no longer aqueous, what's its concentration? It doesn't have a concentration. It's not dissolved. In other words, if we're constantly taking it away, it's constantly driving the reaction to the right. So Lucia Talia's principle tells us that a reaction will always work in the opposite direction of a change to restore equilibrium. So, and it's tough to know how to write that in this space. But what I'd say is this. If we increase the concentration of A, or if we add A, it's going to shift right. And you're going to see me use that language a lot, talking about shifting direction. Does everyone know what I mean when I say this reaction shifts right? Hands up if you don't. This is a good time to be honest. What I mean when I say it shifts to the right is that the reaction will make more of the products. So the reaction is going to move so that it's making more B than A, just for a little while. And then once it's done that enough to counteract what I've done, equilibrium will be restored. If I add B, it will shift which way? Good. What if I remove A? It should shift left. And what if I were to remove B? It should shift right. Now, I stuck with an example here that only has one reactant and one product. Would all those things be just as true if there were 2 reactants and 2 products, 7 reactants and 11 products? You bet. So again, I don't know if that's a great explanation, but it's kind of the best I can come up with here. Now I want to look at another example. We've been talking about aqueous solutions. What if I had some reaction where 2A reacts with 4 of B to make 3 of C? And these are all gases. The pressure a gas exerts depends on what? Pressure depends on what? Pressure is what we're measuring. If I wanted to increase the pressure, assuming I have to keep the volume the same and keep the temperature the same, if I wanted to make the pressure of the gas higher, I could only do it by adding more gas, more molecules. If I wanted to make the pressure lower, I would have to make fewer molecules. And if you remember, I know this was a while ago for you guys, but if you remember, when we did that lesson on ideal gases, we said it doesn't matter what gas it is. Do you remember that? So 1 mole of hydrogen, which is the smallest gas, exerts the exact same amount of pressure as a mole of radon gas, which is really big and heavy. The pressures are identical. Can you picture that? It depends only on how many moles there are. So if we look at this reaction, which side wants to exert more pressure of the reaction? A and B, because together there's 6 moles of gas if we let the reaction go all the way to the left. If we let the reaction go all the way to the right, how many moles is it? 3. Now, like any other reaction, this will form an equilibrium. So at a constant temperature, it will reach a place where the reaction goes back and forward to a place where it is comfortable and steady and happy and stable. But now I want to say, what if I took this and I put it under more pressure? Well, just like the little kid, Lucia Talia's principle tells us that the reaction is going to try to undo what I've done, right? So if I am increasing the pressure, the reaction is going to try to decrease the pressure. Does that make sense? Okay. Which way would it have to shift to decrease the pressure? Have to shift right. You see that? Because on the right side, when it moves right, it's constantly decreasing the number of moles of gas. And in decreasing the number of moles of gas, it's decreasing the pressure. What if I decrease the pressure? Now Lucia Talia's principle tells me that the reaction will try to increase the pressure. In which case, here it will shift left. So if I increase the pressure, it's going to shift to the side that makes less gas to try to counteract what I've done. If I decrease the pressure, it's going to try to increase that pressure by shifting to the side that makes more gas. So if I decrease the pressure, it will shift left. And I'm just going to say here, that makes more gas. And if I were to increase the pressure, it's going to shift right to make less gas to counteract what I've done. So if you can just imagine chemistry being like a stubborn child, which shouldn't be too big a stretch for most of you, I don't think, you'll understand Lucia Talia's principle. I'm sure in grade 11 chemistry, I talked to you about the Haber process. Except you guys, because I never got to it last semester. I just ran out of time. but Fritz Haber, the person who discovered how to make industrial fertilizers. Oh, did I not? It's an amazing story. I don't have time to tell it now, but you should read about him sometime because he's fascinating. He basically single-handedly prevented Europe from starving to death because the population had grown so large that they couldn't keep the crops going. So he learned how to make nitrogen-fixing fertilizers in the lab. But then it's this horrific, tragic story because in the First World War, he actually is the person who develops the chemical process to produce mustard gas. And he's actually out in the field launching this at his enemies. It's really tragic, and I invite you to read about it. But did we talk about that?
Yeah, now you're talking about the mustard gas.
Yeah. Cool. But for him to make this reaction work, he had to provide huge pressure, and he had to provide huge temperature, which is what we're going to talk about next, to make the reaction actually go the way he wanted it to go. And this is why. We talked about that last year kind of vaguely, but Le Chatelier's principle explains why, which is when he added pressure, the reaction he's making happen favored the side with fewer molecules of gas. And that happened to be the thing he was looking for. And then he also changed the temperature. And I want to imagine now a reaction where we have A reacts to make B and a whole whack of energy. Now, just really quickly, what can you tell me about that reaction looking at it? It is exothermic, releases energy, good. And it's going to release that energy realistically as heat. Okay. So A breaks down to make B, and it releases heat energy. Okay. Now again, eventually at a constant temperature, this will reach an equilibrium. Right? So it will reach a point where A gets produced at the same rate that B gets produced, and it's nice and steady. What would happen if I made the reaction system hotter? Well, Le Chatelier's principle tells me that if I make it hotter, the reaction is going to try to make it colder. Which way would this have to go to make the reaction colder? Have to go to the left. So instead of trying to memorize, oh, okay, if I heat it up, it should favor the endotherm. If I cool it down, we're going to memorize it. Picture the reaction, a stubborn little kid, desperately hanging on to that shopping cart. And if you can picture that, you'll understand what to do. Now again, what if I took this reaction and I made the whole system that was happening in cold? What's the reaction going to want to do now? It's going to want to make it hotter. Which way is the reaction going to shift that? To the right. So if you understand the reaction as undoing what you've done, together. And again, this is also an equilibrium, obviously. And again, we would say, if I increase heat, it will shift which way again? If I increase the temperature, it would shift left. It would shift left to use that heat and get rid of it. If I decrease the temperature, it will shift right. And again, all these shifts are temporary because eventually the shift isn't temporary, but the reaction changing rates is temporary because it will eventually reestablish equilibrium. The last thing I want to mention is that catalysts don't affect equilibrium because yes, they speed a reaction up, but the catalyst actually speeds everything. It speeds both of them up. So the catalyst does speed up the forward reaction, but it also speeds up the reverse reaction. So is that going to change the equilibrium point? No. Now, interestingly, a catalyst will make a reaction come to equilibrium faster, which is useful for us, but it won't change the equilibrium point. I hope today's lesson made some kind of sense. A lot of material, covering a lot of stuff. This unit goes pretty quick. Right? It's a speedy one. And yeah, so I'm going to put some homework up on this, but they're largely questions like this. There's a handful like the first one, where you have to calculate K, Q, or you have to write the equilibrium equation. Then a lot of it is just this second bit, where I say, what would happen if we changed this? What would happen if we changed that? Fair? All right. that enough hole punch, please? Sorry. Oh, I should stop my broadcast, I suppose.